Okay, so we have a center of mass on the beam. We have an axis of rotation up here. Might not even be an axis of rotation, but it's an axis. Okay? What's the moment of inertia of this thing about this center of mass? Okay, well, here's the beam. And it has a moment of inertia about the center of mass. Which is very easy. Calculate the center of mass, then just do all your MR squareds, or do an integral or whatever. Okay? But the idea is simple. Just think discrete masses if you like, and then you can generalize that to a continuous mass distribution if you understand how to partition things and so forth. If not, they're formulas. Okay. What's the moment of inertia of this beam relative to this axis? What's the moment of inertia about this axis? Well, it turns out it's fairly straightforward, whether you totally understand it or not, because I'm not going to derive it, because it's enough to get your head around it. Okay, we don't want to go to a ridiculous extent, although you can kind of read it in your book. They do a pretty good job with it, I think. Here's going to be your R vector relative to this axis. The R vector from here to the center of mass. Okay? Now, the total mass here add up all your masses, total mass, right? That makes sense? So what's the moment of inertia about this axis? Because this thing's flying along here, it's going to collide with something else that's rotating about this, and we need to figure out just how that's going to work out, okay? Well, moment of inertia about this axis is just the sum of the moment of inertia about the center of mass at this point, right? I was going to write this down in symbols, but I've got to do more stuff with vectors. So I'm just going to write it out in words, and we can worry about the rest of it later, because we want to get the concept anyway, okay? So moment of inertia about the center of mass plus this. It's like we concentrate all the mass at the center of mass and just get the moment of inertia of a particle, okay, at this position. That makes sense? Just like you concentrate, okay, if you want the torque about a point on the beam, you do it as though all the mass is concentrated at the center of mass. Well, for similar reasons, you treat this as a particle with all the mass concentrated here at some distance, okay, or at some position defined by your r vector, right? Okay? And you add that to the moment of inertia of the mass distribution relative to the center of mass, right? Everything's relative to the center of mass. Okay, so well, I could write this as a formula. I was going to. That's actually confusing a couple of issues there. Okay. When I said I didn't want to do that, and I decided I did. And that's our ax. I was thinking angular momentum because that's the context in which I was kind of talking about it, okay? So that's just a little over the hill confusion on my part, but that's it. Okay, now everything I wrote down is correct. Moment of inertia, the center of mass. And I should have written about this axis of rotation. And that equals just this. So the whole idea is you can break the moment of inertia of all these masses relative to this. They're all at different r's, right? So I could, if these are discrete masses, I could do the mr squared for this one, the mr squared for this one, and the mr squared for this one, couldn't I? Okay? It's not necessary. If I know where the center of mass is and know what the masses are, I just say, okay, concentrate all the masses here, and that averages it out, in a sense. Okay? It's a big deal.